Greetings. I am sorry I cannot be with you in person, but I'm grateful for the opportunity to send you this recording. My name's Nicholas Heyman. I'm the director of the Oklahoma Geologic Survey. I have known Kichiro Kawamura sensei for many years and have had many submarine and oceanic expeditions with him and his colleagues, and am grateful for this opportunity to update this community on our work here in Oklahoma, where I've been since about 2020. This is a group effort. Netra Regmi is a geomorphologist who is the head of our environmental geoscience group. Kevin Blackwood is a hydrogeologist with experience in wind energy in particular. Cecily Ray is our GIS specialist, has been very helpful. So this is a group effort. On the right in this slide, I took a picture from Connecticut where there's an offshore wind development was occurring about 2 years ago. And then on the left is a picture from a highway in Oklahoma where you see a ridge line with wind turbines on it. And what I'd like to do in this talk is I'd like to try to connect some ideas about onshore and offshore wind geosciences, starting with an overview of wind energy in the United States, and then zooming in on Oklahoma, as the famous musical says, where the wind comes sweeping down the plains. Then we'll look at geology field siting in Oklahoma and kind of think about how we use geology to consider how these are deployed. Look at the natural hazards, and then try to connect some lessons between the two. And you'll see at the bottom right of the slides, where available, there will be some index to where in this talk we are from 1 through 5. So let's talk about U.S. major energy sources in general. On the right is a plot going up to today where we see basically renewable additions of wind and solar and other renewable energies, but wind is a prominent multiple percentage of the U.S. annual energy capacity. And you'll see it goes up and down, and in fact in 2023 there was a decrease from actually low wind speeds, but also some changes in the infrastructure. But you can see how they're distributed in the U.S. These dots all represent, on the left, the dots represent wind farm locations throughout the U.S. And the reason we have those distributions of location of wind energy, of wind turbine placement, is because of the wind. We see along the mid-continent, going from Texas to north through the Oklahoma and other areas, the highest wind speeds. And so as a result, that's where a lot of the wind turbine placement is. And similarly, the black and kind of dark green bars in the bars of the cumulative plot of regional capacity for the U.S. are Texas in black, and then the mid-continent in that kind of greenish color. In fact, Oklahoma comprises a big chunk of that. If we move forward, we can see then that wind turbine distribution is clustered in parts of our state in Oklahoma. In fact, this is true for the U.S. in general, that there's kind of an east-west divide in the power system, largely driven by the landscape. And this cluster of high transmission lines sit over what we call the Anadarko Basin, one of our large basins, and the Panhandle. If you imagine this as a pan, there's a handle, that thin strip in the very northwest of Oklahoma. That becomes your power, high transmission line power infrastructure. And the red arrow is pointing down towards the Gulf of Mexico on the other side of Texas. So if we go forward a slide, we see the red arrow is continuing into Texas from Oklahoma, and there is where offshore wind development plans are happening for our nearest shore. Obviously, the Atlantic and Pacific also have plans. But in fact, today, there has only been some talk of 4 lease areas where companies could build offshore wind, and one area where there's a purchased lease being developed. But as you can see, offshore wind in the Gulf of Mexico is in terms of number of turbines or active projects behind the onshore distribution of wind turbines in Oklahoma and Texas. So this is a note to kind of give some perspective on where wind energy is in the U.S. However, wind is important, very important for energy. It's the 11th, basically, if we look at Oklahoma, not the U.S., so we're zooming in on Oklahoma, it's the 11th in energy use per capita, so we're an energy use intensive state because of our industries primarily. We're the 4th in the storage capacity of renewable resources, so we actually are quite a leader in renewable energy. We're the 6th in the nation of all electricity, just electricity produced from wind, solar, and energy. 41%, 0.7% of our energy is renewable produced. 2023, 45% of the electricity used in the state was from renewables. And then you can see other statistics about the number of homes, the number of jobs, and how much the CO2 offset is from wind energy, basically offsetting about 30 million tons of CO2. So it's an important component of the renewable energy portfolio of the state of Oklahoma. It makes money, $27 billion of storage projects, annually $150 million of tax revenue, and including payments for leases to ranchers and farmers and private landowners who lease their property, and saving a lot of water. Basically water is saved by producing energy from wind and renewables. These are all data from the EIA. They're not Oklahoma data. They're data from a 2024 EIA report. The wind energy, basically Oklahoma is the 3rd in the U.S. for wind energy generated electricity, and 94% of the renewable generation is actually wind. So we're a leader there. If we think about the U.S. Department of Energy, the federal partnerships, you can see on the right there are many projects, including universities in Texas and Iowa that have developed wind projects in Oklahoma, and the largest being this NREL, distributed wind testing facility. Okay, let's talk about geology a little bit. And this doesn't seem like an obvious geology slide, but what do you notice? That the distribution of wind turbines, the large facilities, follows this northwest southeast trend along these kind of streaks. And the reason for that is geological. We look and we see these ridge lines tend to have the turbines on them, and these ridge lines are northwest southeast oriented ridges. And that's a geological control. It's actually from the ancestral Rockies, something like 300 million years ago, when Africa and North America collided. Far away inland in Oklahoma, ridges and basins formed, and today still remain. Of course, it's always more complicated in geology, but that's a simple way to think of it. If you can imagine 300 million years of history, you can explain to yourself why wind turbines are distributed like they are. For example, in the Slick Hills, these red dots here, there were many studies that the Oklahoma Geologic Survey did to think about wind development. And this study was actually done quite a long time ago, in 2002. Here's a slide, a picture of an area in north central Oklahoma, again, looking at these ridge lines and how they're distributed. And we can see that the result of this kind of study did in fact lead, as this 2013 article shows, now over a decade old, that the big Watonga Wind Power Project, one of the large flagship projects in Oklahoma for wind, was developed along one of these ridge lines, targeting that kind of landscape. So the Oklahoma Geologic Survey considers geohazards when we look at wind development. Think, for example, of landslides. Now, most people think of Oklahoma as very flat. I showed you a slide that shows you it is not flat. There are ridges, and these ridges are important for wind turbine distribution. They're also important because they tend to be very soil rich and weak soil, and we have many slow and small landslides, some that can speed up, but it's a very complicated environment for slow slipping landslides that are rooted very shallowly. And we've actually done some work with remote sensing using with some support from NASA, the U.S. space program, looking at with their Earth science program, looking at how to use machine learning to map landslide susceptibility. And you can see here this figure in the center is from a paper by Netra Regmi looking at that landslide susceptibility along these ridges. And you can see where in the state these kind of cluster, although they are widespread. Again, a consideration for siting wind turbines. Another one we look at is karst topography, where there are carbonates. If you look in this map from the Geologic Survey, on the right are these blue patches, are the widespread karst topography, where carbonates are dissolving and creating subsidence and sometimes caving and hazard. On the left is the more salt-dominated environments with its own problems of subsidence and dissolution. Sometimes there's karst systems under salt. It can be quite complicated. But what you see is that if you do not consider hazards just from that landscape, you can wind up rerouting roads, having disrupted collection lines on the energy, and tower foundation issues. Here's an example where there was a site that had distributed wind turbines, very advanced project, but because they did not consider some of these hazards, there was a lot of forced relocation of turbine locations, a lot of engineering costs that were incurred because the geology was not honored in the beginning. And this gives you a sense of the really exciting kind of work we do when we look at these problems. We get out in the field and look at the karst topography. Here's slides of Kevin Blackwood looking at karst topography at a site, going in a cave system underground to look at the stability underneath the karst, underneath the turbines, and mapping these kind of distributed landscapes. We also use geophysics. This is a ground penetrating radar result that then had some field ground truthing to look at the causes of an anomaly in a ground penetrating radar image from a possible wind turbine location. So let's summarize the lessons for offshore wind development and geohazards. Onshore wind energy deployment is significant in the U.S. and done independently of offshore plans. We see that by comparing the Gulf of Mexico to Oklahoma's distribution. Wind energy production is at a significant level. It's tens of % of the renewable portfolio for our area, and produces comparable energy to offshore wind right at the moment, more than that for the United States. It's susceptible to wind speed variations and geological and topographic features. That's a really important point, one that I think is transferable to offshore wind geohazard siting or assessing, that basically we do look at how geology and wind turbine distribution are related to one another. And it's an example of large wind energy deployment in Oklahoma. And we see several unique aspects to the geology and geohazards. First, we see these tectonically produced ridges are compatible with the wind energy distribution. They just control the distribution of the turbines, but the wind itself cuts across those ridges and produces the energy. There's abundant shallow landslides that we do have to consider. That's clearly relatable to offshore siting. And we really use things like machine learning, remote sensing, and then ground truthing to look at that impact, including that of karst and salt systems, which also is an important component for offshore siting, particularly in the Southwest Pacific and Asia, where carbonate systems start to come in as you move south. Tools currently used are machine learning, remote sensing, geophysics, and ground-based geology. It's just like all the rest of the earth sciences. We observe, we assess, we map, we interpret, we hypothesize. It's an exciting field. I think all of these topics of energy, whether they're dealing with renewables or sequestration of carbon dioxide or alternative fuels or storage of energy, in battery technology. We know that the future is uncertain. As Yogi Berra said, it's tough to make predictions about the future. Or as he said, it's tough to make predictions, especially about the future. But plan for the future, because that's where you are going to make the rest of your life. Thank you very much, and I hope you enjoyed this presentation. Please contact us anytime. We're easy to find. It's my last name, Hayman, Hayman, at ou.edu at the University of Oklahoma in Norman and the Geologic Survey of Oklahoma. Thank you very much.